Okay, so hello and welcome to this brand new coding session of me implementing a HTTP server from scratch in C. Yesterday we left off with implementing the multi-threaded server. We also fixed some bugs in file caching and finally got something that can serve out static files to the internets. And today we hopefully will finish the multi-threading of the server. Yeah, let's just go ahead and start. So open a new tmux session. Oh no, tmux. Go ahead and open a new tmux session and open NeoVim. Let's first revisit where we were. So we were trying to spawn these threads here. Also, this closing of the server, I'm not very convinced that this is the way we should do it. And also there's a bug. So maybe first of all add that to our to-do list. Revisit the closing of the server. And because it's not even correct at this point in time, okay, so here we did go ahead and said give it the args and start accepting connections. And for some reason this did not work. And I also don't quite know how we best debug the multi-threaded, okay, that took a while, the multi-threaded server. Handle requests. Okay, so now close socket descriptor. Okay, so we first have to make debug mode 1. Holy shit, we're slow today. Okay. Kinda slow today. Handle requests. Okay, now it works. Can GDB freeze threads? Thread. You can choose whether to set breakpoints on all threads or on a particular thread. So this obviously is something we want to do. So del 1 and then break the handle requests on thread 1. Okay, I don't even know which thread. Okay, so it obviously was the wrong thread. Okay, GDB show threads. Okay, so maybe we have to break where we spawn the thread. So break 3, 4, first info break. So break at 3, 4, 3, 4, 7. Run. Info threads. So break handle requests on thread number 2. And del1 info break del3 continue. Okay, so we never hit this. What does even, so it just crashes. Nice. Oh no, it doesn't crash because we just return 0 and never. Okay, so that's obviously bad. So we need some signal here. Const t pthread const init. It also needs a mutex. So I wonder if this is actually a good way of doing it, or if we're just poking around here. But this would be a way of signaling. So I think we remove this here, and even this. Wait for signal thread. Conditional wait. So we need a mutex. So let's just try it. Let's delete this one as well. So give back the control to the thread. But I don't really know if this actually spawns a new thread. I don't know. Okay, so let's say this is a pthread const t kill signal. And we have to init it pthread don't know if we can even do this here. Probably not. Signal sigint to threads. Is there a pattern to do this? Yeah, so they do it like this as well. Okay, so we have a const t, but probably this thing has to be initialized somewhere. I mean, you can't just have this mutex here. Okay, so how do we do this actually? I mean, we can't really initialize it in outside a function. I mean, if this thing is not initialized, then we do have a problem. Okay, so maybe we initialize it before this. So pthread const init, and then the kill signal. This can return, so if return -1. a non-zero codon error. So if this is not equal to 0, and we also want to destroy this thing. I don't know where we want to destroy it right now. Maybe even here. Or now, maybe not here. So pthread signal, const signal. Wait a second. Pthread const signal, we say the kill signal. This can return an error, but I think we just ignore that error. So so here when we spawn the threads, I mean we can basically receive it at any time. Pthread can't wait, so we also need a mutex. So we have to lock the mutex. Pthread mutex t kill mutex. So we say we want a pthread mutex lock mutex kill mutex. Unlock it. I mean, these threads can also have a problem or run into problems. So we have to acquire the mutex pthread mutex. No, pthread lock. Should it lock should the main thread lock it? So if pthread mutex in it, I guess. So we have those two. We knit the cont, and when we did serve, say pthread mutex destroy kill mutex and pthread cont destroy the kill signal. We also have to acquire the mutex here. The kill mutex, pthread lock mutex. Have to acquire the mutex, and here we have to unlock the mutex. And these can all return errors. We directly lock it. Here we want to the kill. So they probably, okay, so they know about them because it's a global variable. So we want to lock it. We want to, so if we can't lock it, we just return. If we can't do this, so this will acquire the mutex again. In serve, this can't wait here will acquire the mutex. If this is not equal to 0, return -1. And when we receive the signal to kill all the threads, we obviously need something like this here, pthread thread handles okay. So we have all the thread handles. We create them. If we receive the kill signal, we want to say for int I 0, I is less than end threads plus I. What the heck is going on? If pthread, I think it was kill thread handles at I is not equal to 0. So what is going on with my indentation here? Is this correct? Try to kill them all. And I don't know if this even works. So even if this returns a -1, okay, so then we should destroy this. So at cleanup, when we have a generic cleanup, then shall we have a generic cleanup? I mean, at this point, the arena even has been initialized. Even at this point. How do we do this? So server cleanup, go socket descriptor. I mean, this might be initialized. So destroy program memory. I mean, if this fails here, then We need a red val here. We just return this, blah, 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 blah. So socket, if this fails, we return -1 as well. But if this here fails, we just set the red val to -1 and go to server cleanup. So here as well, so red val is equal to -1, go to server cleanup. Even here, the file cache has to be destroyed as well. Or does it? Does it have to be destroyed? No, it doesn't have to be destroyed. So this is also red val is equal to -1, go to server cleanup. We could also just use the function here, but red val is equal to -1, go to server cleanup. The same thing here, red val we just try to do this. Destroy the memory, and that's it. So if this has if this is a -1, so this could already send while this is not even listening. Yeah. I don't know. We have to do it this way. Return red val. we can't unlock it, okay. Pthread what is it called? Pthread lock pthread lock mutex. What was it? It was the unlock. Pthread lock mutex? What is this? Pthread can't destroy. Pthread mutex unlock. Pthread mutex destroy. Pthread mutex init. No. Lock. So if we initialize this, so this is, if we already initialize it, yeah, I don't know. So this is probably not the best way to do it, but okay. Pthread lock. Pthread mutex unlock. Single. Signal. Pthread can't init. Pthread can't init. Pthread mutex init. Thread handles was not declared in the scope because it was not declared. Because it was declared here. Yeah, we don't even need the scope here. Process the initialization. Yeah, so this is the next problem. we would have to put them at the very beginning. So I suppose what we could do is make the scope bigger. So now thread handles should be declared. Oh. This is obviously also wrong. Socket descriptor was not declared in the scope. So now it runs and it exits, but I don't know. Okay, so let's try to debug this. So run, break, handle, no, break, handle info threads, no threads. I think it should be 2. So break. No, we first have to spawn them. 3, 4, 8, run. Info threads, break, handle requests on thread number 2. Info break, delete the first one, continue. Unfortunately, it didn't work. So the question is, if I now say curl-x get localhost index.html, it returns something. So did we do it? So it seems like we did it. So when we sent the signal, no. Does this work? So we lock it, we sent the signal, and this let's read this. Restarts one of the threads. And waits for the condition variable to be signaled. The thread execution suspended, does not take before returning. Pthread can't wait, reacquires mutex, unlocking the mutex and suspending. It's done automatically. Thus, if all threads always acquire the mutex before signaling the condition, this guarantees that a condition cannot be signaled between the time a thread locks the mutex and the time it waits on the condition variable. Thus, if all threads always acquire the mutex before signaling the condition, so we lock it, this waits for the free, but it reacquires it, doesn't it? For signaling the condition. So do we need this unlock here is the question. Do you need mutex unlock after signaling? This guarantees that a condition cannot be signaled between the time a thread locks the mutex and the time it waits on the condition variable. Yeah, it would be ignored if it wouldn't lock the mutex. So now it has to wait. Now it has to wait for the mutex to be released by the count wait, and thus we wait here until it actually waits. Then we signal it, and then we unlock. I don't know if this unlock is actually necessary in this case, but it works. So in theory, we now have a multi-threaded HTTP server. That should be capable of one second. So this should be capable of serving sites on multiple threads. So that's actually nice, I guess. Let's see if we have. So I think the multi-threading is actually done now. So let's add all to our Git. Feature multi-threaded server. Push it. Okay. So now, what is next? What shall we do next? HTTPS? Well, let's look at our to-do list here. Transfer encoding. This may be fixed. Compute the hash for common headers. We have to. That we did also. So transfer encoding, I don't know if this is actually worth it. Error handling could be something we can look into. maybe we continue reading the RFC and see what we might miss at this moment. So we have this request target, and all of these things here we did not do. So we have these different forms here, that is origin form, absolute form, authority form. We have actually none of this. None of this is actually implemented, so there's no parsing. That is something we have to do, probably. So parsing of the request target. That is something we have to do. When a proxy receives a request with an absolute form, blah, 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 blah. Okay, so all these different forms. Then we have the status line that we put back with the status code. Field line parsing we have done also. So obsolete line folding is something we do not do. Must be extended over multiple lines by preceding each extra line with at least one space or horizontal tab. Okay, I don't even know what that means. Optional white space, current return line feed. What is the RWS again? Required white space. Except within the message HTTP media type. I'm not very obsolete line folding. Message body, this can have some transfer encoding. Message body length. The length of a message body is determined by one of the following in order of precedence. Any response to a head request and any response with a informational no content is always terminated by the first empty line after the header fields, regardless of what? Okay, so we don't even implement head requests. Connect. If a message is received with both the transfer encoding and the content length field header field, the transfer encoding overrides the content length. Such a message might indicate an attempt to perform request smuggling or response splitting and ought to be handled as an error. An intermediary that chooses to forward a message must first remove the received content length field and process the transfer encodings. Okay, we just reject these messages when both are there. Must respond with a bad request. If a valid content length header field is present without transfer encoding, its decimal value defines the expected message body length in octets. If the sender closes the connection or the recipient times out before the indicated number of octets are received, the recipient must consider the message to be incomplete and close the connection. If the sender closes... or the recipient times out before the indicated number of octets are received. So yeah, this is something we also didn't implement because, okay, so this is actually something quite bad. What if the content length exceeds 8,000, the content length plus the header size exceeds 8,000 bytes. This would lead to a bug. So in here, we read into the buffer, and this is 8,000 bytes. So in case so parse HTTP request. This should only parse the header, and it should return the number of bytes it actually read. So in http.h, parse HTTP request. We probably just parse the header. Parse HTTP request. I mean, we set the message body. Maybe we should return a pointer to, maybe we don't return an I16, but a pointer to the start of the message body. So this is the start. We don't set the message body in here, but so if this is less than 0, we just return a char star -1. Or maybe it should be a void star. No, it can be a char star. And else we return the message body start pointer. Okay. So if the message body start pointer, I wonder what the message end pointer is again. So if the message body start pointer is greater than or equal to the message end pointer, so we don't need this here. Now we have to change the header file. This is a char star now. Parse HTTP header. And now go back into our main. And this is now if, so let's message car star message body start. Is equal to this. And if the message body start is equal to car star -1, this is the case. So if the content, now we have to check whether there is a content length and whether we have to read again. And also when we have transfer encoding, this would so this thing is probably a little bit broken. I think we have to pull this one out. And then we have to read until we get a 0. Especially when we have transfer encoding, then we don't even know how big the message is. Okay. So I will grab a tea and be right back. And then we try to implement this. Okay, so this for loop actually doesn't even make sense here. So let's hoist this out. So this is the max HTTP header size. I mean, we can remove the entirety of this for loop. Okay. So we want to parse this. If we don't have this, we return something, and if there is something, so if we also would need the red bytes here. So if the red bytes is equal to max HTTP header size, we have a problem, because we need this to be larger. I mean, we could also say that we make this max HTTP message size. No. How do we do this? So there might be, it might not send everything at once. Or does it? When if the content length indicates that there's something, how do we do this? What even is the problem? So we issue a first read. This read should, in theory, get us the header. Where does it issue the reads? Pass HTTP request. raw request. So where is that coming from? Handle new connection. Handle client request. Wait for client request. So they have a max request size. They receive this, but they have no loop. What if it sends something later? Can that happen? So let's say max HTTP message size. Max HTTP message size. We could also parse the header first, and then if we look at the specification, it says defines the expected message body length in octets if the sender closes the connection or the recipient times out before the indicated number of octets are received. The recipient must consider the message to be incomplete and close the connection. So this indicates to me that attempts to read up to count. So I think so read does that for me. It reads until end of file. And then we could say that this really is something like this. And we don't really need the okay, so this would inevitably mean that we only read once into this buffer, and we say this is the max HTTP message size, max HTTP message length. So we only read once. That makes it a lot easier. We could implement a should we just return message too large? Max HTTP message length. And I think this I don't really like how we do this, because now we don't have the restriction on the header. Now we don't have the restriction on the header. That is 8,000 bytes. Yeah, if the content length indicates that, so if the content length is greater, is there a too large HTTP request entity? The limits defined by the server. Okay, so 413 would be this too large. So in HTTP we define too large as 413. And we say too large response for 13. And in our http.cpp and in the lookup status line, we have too large return too large response. Okay. So we could split it up. But then, I mean, this would only be the case if we would implement this in a way that the server is concurrent. And we have to check whether we can read something or not. Yeah, I don't know. To do move this into a table. I mean, we could try it. We could try to 1 second. So we could try to read for. So let's actually try to make a concept of this. So we get some. I mean, read will try to read until an end of file, or until the buffer is full. So in the end, if we make a restriction on the max size of this, then yeah, this doesn't make a lot of sense, I guess. What we could do is just for the header not scan. So let's say we receive a very large header and we say our header is basically 8,000, restricted to 8,000 bytes. So let's say, okay, so we get a message. It's HTTP message. And it has a very large header that exceeds 8,000 bytes. So its header is greater than 8,000. Would this be a problem if the header is 1 megabyte? I mean, always reading 1 megabyte, kind of bad, especially for GET requests. So but also for transfer coding, what do we do if someone So if it is full, when we issue a read, and let's say someone uses transfer encoding, which we don't even support at this point, or even it's larger than 8,000. So we read, let's say we read onto the socket file descriptor and we read with 8,000, not 80,000. And let's say this is full. The buffer needs to be in here as well. And let's say this returns. Where is it? Where is it? My mouse is gone. Oh, okay. Let's say this buffer gets completely filled. Buffer full. Then we probably have to issue a second read to see if there is... No. We issue a first read for the header. And so we issue a first read for the header. Header read 8000. And if this returns, if this already is bad, then we don't have to issue the second read. But if the returned bytes is 8000, then we have to issue a second read with max HTTP size. HTTP message length to see whether there's still something in there. Or we can even poll. We could even poll. Okay. So let's try to implement this. We issue a first read. But also the problem is that when we issue a first read with we would have to also copy the contents over. So if you read into one buffer and then read into another buffer, or we could also read into the same buffer with the offset. So we could say something like in HTTP, let's say const expr db header length 8 times 1. Okay. And then in our main we read, but first we read max HTTP header length into the buffer. And then we try to parse the HTTP request and we check whether the host header is there. And now we want to check whether there's still something to read. And that we can read into the max HTTP message length. Oh. It waits for one of a set of file descriptors to become ready to perform performs a similar task. It waits for one of the set. No, so this is not what we want. Linux check whether file descriptor has content. But here it says it wants to wait. The timer argument specifies the number of milliseconds that poll should block waiting for file descriptor to become ready. And this should only, we should only do this if the content length indicates that there's something to read. No. So Paul, what does it return? What does it return? Number of elements in the Paul whose read events fields have been set to a non-zero value. Should we poll? I mean, we should only poll if there's actually something to read. So if read bytes is equal to max HTTP header length, we check whether there's still something to read. It also does select all of these requested events, returned events. I mean, I'm not sure how we do this. So when we read, should we read the entire thing? Then this would work. But if we say we want to read just the first 8,000 bytes, this would not work. So we could, so if read bytes equal to max HTTP header length. No, I think this doesn't even make sense. Max HTTP message length. Does it make sense? I mean, in which case does it make sense? Reading 8,000 bytes is obviously cheaper than reading 1 megabyte. And if the header is already corrupt, then why would we read all of the rest? Yeah, so I think this... I'm kind of... If read bytes is equal to max HTTP header length, then we want to issue another read. With max HTTP message length minus max HTTP header length. So I32N so if this is the case, I think we can just increment. No. I mean, if it... This is kind of hard. If... So first of all, if n is less than or equal to 0, now if it's less than 0, so if n is greater than 0, we have to do something with the message body. So if there is a message body, if the how do we call it? If the request message body dot pointer if there is one, we just say request message body dot length plus equals n. Else, if there's none, message body pointer is equal to buffer plus max HTTP header length so at this point we already have a valid message, I guess, and n. So we have the opportunity to read a little more if the payload is a lot larger. And I think we somehow have to test this. Curl file as message body. Data binary. Okay. Request dot message body. Okay. So this still works. Let's make it verbose and make a post. Connection refused. Okay, so this works. So let's make GDB HTTP server and let's break at 223, run the thing, and then so let's try to make this a file and yeah, and large file. Okay. So lsla large file. Still not large enough. So now it's a officially large file. And curl add home root personal HTTP server large file. Okay, so p max p read bytes 8 times 124. So we read again pn. So this seems okay. If n is greater than 0, p message request dot message body, content length of 4996. Yeah, so this is correct. Git status git add dot, oh no, git status git restore staged large file git commit dash m feature support for larger payloads git push push origin master. So this seems correct now, I guess. Obviously this requires another branch, but I think this is the better way of doing it, because we only have to read the 8,000 bytes, and if the header is already corrupt, then it's already lost. All bets are off. Okay, again, my cam trying to fool me. Yeah, so this is also something we can take off the to-do list. And handle post too large. Maybe we look into HTTPS. So here, connection management, handling incomplete messages. Server that receives an incomplete message, usually due to cancelled requests or triggered timeout exception, may send an error response prior to closing the connection. So incomplete requests, I just return an error. We will not wait for anyone to send us more. So let's read this part of the specification. It's independent of the underlying transport or session layer. Only presumes a reliable transport with in-order delivery of requests and the corresponding in-order delivery of responses. The mapping of HTTP request and response structures onto the data units of an underlying transport protocol is outside the scope of this specification. Blah blah blah. Um, Establishment. It is beyond the scope of this connection are established via various transport or session layer protocols. Yes. Persistence. Multiple connections are typically used to avoid the head of line blocking problem. We usually have some timeout value beyond which they will no longer maintain an inactive connection. I mean, I just close it. I just straight off close it in my implementation, I guess. When we handled it. Yeah, we just straight off close it. Which may or may not be good or whatever. But okay. So then if we try to implement some connection management, we would also have to consider timeouting the connection, which I don't want to get into right now. Close messages and timeouts. So this would require concurrency. This would require concurrency. So conceptually, HTTP TLS is simply sending HTTP messages over a connection secured via TLS. The HTTP client also acts as the TLS client. It initiates a connection to the server on the appropriate port and sends the TLS client hello to begin the TLS handshake. When the TLS handshake was finished, the client may then initiate the first HTTP request. All HTTP data must be sent as TLS application data, but is otherwise treated like a normal connection for HTTP. TLS uses an exchange of closure alerts prior to non-error connection closure to provide secure connection closure. When a valid closure alert is received, an implementation can be assured that no further error will be received on that connection. When an implementation knows that it has sent or received all the message data that it cares about, typically by detecting HTTP message boundaries, it might generate an incomplete close by sending OK. Can be used to enclose a single HTTP or response message. Because of the line length limitations, field values within are allowed to use line folding. Okay. Line length. Okay, so OpenSSL. Let's look into this. OpenSSL TLS. SSL and TLS protocols. Also, something we want to implement is probably logging. AFL fuzzing. I have no experience at all with OpenSSL and using it. TLS. We should probably read this. So there's TLS introduction. TLS. Okay, I think we have to do some reading on this. Let's read the introduction. Transport layer security. Transport layer security allows applications to securely communicate with each other across the network, such that confidentiality of the information exchange is protected. Additionally, it protects the integrity of the information exchange to prevent an attacker from changing it. Finally, it provides authentication so that one or both parties can be sure that they are talking to who they think they are talking to and not some imposter. Sometimes transport layer security is referred to by its predecessors' names SSL. OpenSSL dates from a time when the SSL name was still in common use, and hence many of the functions and names used by OpenSSL contain the SSL abbreviation. Nonetheless, OpenSSL contains a full-fledged TLS implementation. That is nice. TLS is based on a client-server model The application that initiates a communication is known as the client. The application that responds to remotely initiated communication is the server. The term endpoint refers to either of the client or the server in the communication. The term peer refers to the endpoint at the other side of the communication that we are currently referring to. So if we are currently talking about the client, then the peer would be the server. TLS is a standardized protocol, and there are numerous different implementations of it due to the standards of OpenSSL client or servers. An OpenSSL client or server is able to communicate seamlessly with an application using some different implementation of TLS. TLS and its predecessors SSL have been around for a significant period of time, and the protocol has undergone various changes over the years. Consequently, there are different versions of the protocol available. TLS includes the ability to perform version negotiations so that the highest protocol version that the client and server share in common is used. Okay. SSL was initially developed by Netscape. This is not very interesting. In order for the client to establish a connection to a server, it must authenticate the identity of that server, i.e. it needs to confirm that the server is really the server that it claims to be and not some imposter. In order to do this, the server will send to the client a digital certificate, also commonly referred to as an X509 certificate. The certificate contains various information about the server, including its full DNS host name. Also, within the certificate is the server's public key. The server operator will have a private key which is linked to the public key and must not be published. Along with the certificate, the server will also send to the client proof that it knows the private key associated with the public key in the certificate. It does this by digitally signing a message to the client using that private key. The client can verify the signature using the public key from the certificate. If the signature verifies successfully, then the client knows that the server is in possession of the correct private key. The certificate that the server sends will also be signed by a certificate authority. The certificate authority, commonly known as CA, is a third-party organization that is responsible for verifying the information in the server's certificate, including its DNS hostname. The CA should only sign the certificate if it has been able to confirm that the server operator does indeed have control of the server associated with its DNS hostname and that the server operator has control of the private key. In this way, if the client trusts the CA that has signed the server certificate, it can verify that the server has the right private key. Then it can trust that the server truly does represent the DNS hostname given in the certificate. Okay, the client must also verify that the hostname given in the certificate matches the hostname that it originally sent the request to. Okay. Once all these checks have been done, the client has successfully verified the identity of the server. OpenSSL can perform all of these checks automatically, but it must be provided with certain information in order to do so. The set of CAs that the client trusts, as well as the DNS hostname for the server that this client is trying to connect to. Note that it is common for certificates to be built up into a chain. For example, a server certificate may be signed by a key owned by an intermediate CA. That intermediate CA also has a certificate containing its public key, which is in turn signed by a key owned by a root CA. The client may only trust the root CA, but if the server sends both its own certificate and the certificate for this intermediate CA, then the server can still successfully verify the client can still successfully verify the identity of the server. There is a chain of trust between the root CA and the server. By default, it is only the client that authenticates the server using this method. However, it is also possible to set things up such that the server additionally authenticates the client. This is known as client authentication. In this approach, the client will still authenticate the server in the same way, but the server will request a certificate from the client. The client sends the server its certificate, and the server authenticates it in the same way that the client does. Okay? The system described above only works if a chain of trust can be built between the set of CAs that the endpoint trusts and the certificate that the peer is using. The endpoint must therefore have a set of certificates for CAs that it trusts before any communication can take place. OpenSSL itself does not provide such a set of certificates. Therefore, you will need to make sure you have them before you start if you are going to be verifying certificates. I.e. always if the endpoint is a client and only if the client authentication is in use for server. Fortunately, other organizations do maintain such a set of certificates. If you obtained your copy of OpenSSL from an operating system vendor, then normally the set of CA certificates will also be distributed with that copy. You can check this by running the OpenSSL command line. Okay, let's check if we have that. Okay. This will display a value for OpenSSL-dir. Look in the search subdirectory of OpenSSL-dir and check its contents. Etsy SSL. So there are some certs here. You're expecting to see a list of files typically with the suffix of .pem or .0. If they exist, then you have already a suitable trusted certificate store. You can also use environment to override the default location. Okay. You can test that your trusted certificate store is set up correctly by using this. Okay. Once the comment is connected, type the letter Q followed by enter to exit the session, blah, 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 blah. A TLS connection is represented by the SSL object in an OpenSSL-based application. Once a connection with a remote peer has been established, an endpoint can write data to the SSL object to send data to the peer or read data from it to receive data from the server. A new SSL object is created from an SSL context object. Think of an SSL context as a factory for creating SSL objects. Oh no, factories. I don't want to hear about them. You can create a single SSL context object and then create multiple connections, i.e. SSL objects from it. Okay? Typically, you can set up common configuration options on the SSL context so that all the SSL object created from it inherit the same configuration options. Note that internally to OpenSSL, various items that are shared between multiple SSL objects are cached in the SSL context for performance reasons. Therefore, it is considered best practice to create one SSL context for use by multiple SSL objects instead of having one SSL context for each SSL object that you create. With two bio objects, the bio object is used for sending or receiving data from the underlying transport layer. For example, you might create a bio to represent a TCP socket. The SSL object uses one bio for reading data and one bio for writing data. In most cases, you would use the same bio for each direction, but there could be some circumstances where you want them to be different. It is up to the application programmer to create the bio objects that are needed and supply them to the SSL object. for further information. Okay, we have to probably look at these guides. Open SSL TLS server example. So maybe there maybe we have something to look at here, but yeah. I think we will first look at the blocking client. Finally, an endpoint can establish. Oh, this was not intended. Okay. Once a connection attempt is made by the server, once a connection attempt is made, the server will create an SSL object in the same way for a client and associate it with a bio for the newly created incoming socket. After setup is complete, the TSL handshake phase begins. A TLS handshake consists of the client and server exchanging a series of TLS handshake messages to establish the connection. The client starts by sending a client hello handshake message, and the server responds with a server hello. The handshake is complete once an endpoint has sent its last message, known as the finished message, and received a finished message from its peer. Note that this might occur at slightly different times for each peer. For example, in TLS version 1.3, the server always sends its finished message before the client, blah 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 blah. Okay, the server, even if it's possible that the server will fail to complete the handshake. Once the handshake is complete, the application data transfer phase begins. Strictly speaking, there are some situations where the client can start sending application data even earlier, but we're going to skip over that for this basic information. Okay, interesting. During application data transfer, the client and server can read and write data to the connection freely. The details of this are typically left to some higher level application protocol, for example HTTP. Not all information exchanged during this phase is application data. Some protocol level messages may still be exchanged, so it's not necessarily the case that just because the underlying socket is readable, the application data will be available to read. When the connection is no longer required, then it should be shut down. A shutdown may be initiated by either the client or the server via a message known as close notify alert. The client or server that receives a close notify may respond with one, and then the connection is fully closed and application data can no longer be sent or received. Once shutdown is complete, a TLS application must clean up, freeing the SSL object. Okay, so let's look at the GitHub, and maybe there are examples. Quick. What is Quake? So it's always just the client. Maybe there are examples in here. Examples. No. So let's look at the or to write a simple TLS client based on a blocking socket. Okay. I wonder why this is just the client side and not a server example. TLS server example. OpenSSL. Oh. So this looks good. You can look at this. You may find an up-to-date data example within repository demos SSL echo. Okay, so this here. HTTP 3. So there's no echo. Oh no, SSL echo, okay. Okay, let's look. So there, maybe we just clone this and then look at what we can do with it. So let's git clone HTTPS, or maybe, yeah, git at github.com, open SSL. Yay, great internet speed. May.c, is this the server? Configure server context. Okay, this is gonna be a lot of things to do. Okay, so move open SSL demos SSL echo here. ArmorF open SSL and vim SSL echo. Let's look at this. So we also have some things here. So the basic idea basically was you have some SSL context, and then you have these this SSL objects, and on top of these you have for each connection an SSL object, and for each SSL object you may have these bio objects that allow you to read and write from the transport underlying transport layer. Holy shit, what are they doing here? If this is not a server, blah, 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 blah. Okay, so if this is a server, so first of all, okay, so you need to create this context here. And probably we have to import this here. Okay, so we need some context. We need this SSL object, which blah, 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 blah. If we are Windows, I don't care about Windows. So they create, we bind with server port and listen. Huh? Okay, so these are methods that were defined here. Create socket true. Do they use some global. So create socket. Yeah, this creates a socket. We create some context. Okay. Create context. TLS server method. So they override the function pointer here. So SSL context new. Let's go into our main.cpp. I don't know if we will, if this is all in this file. Serve. So here the socket is created. And we bind the socket, we listen, we build some file cache. Okay, so now we have the problem that it's multi-threaded. Does every thread need a SSL context? I don't know. Okay. So they first create the context. Is the SSL context, is SSL, is it thread safe? Is SSL new thread safe? Can safely be used in multi-thread applications. File not found. SSL new open SSL. Maybe first we create the context. So let's, how do you open a new window? Vim open vertical split, Control W V. Okay. So this, here we open the main.c. So let's see. So first of all, we have to create some context. TLS server method. Oops. TLS server method. Where is that? TLS server SSL method. Okay, so that is probably something that comes from OpenSSL. So include OpenSSL.h. OpenSSL SSL.h. Okay, so in our serve method, create context. So let's create the context. We might do this in a way that we can configure whether it's HTTP and HTTPS, maybe. So okay, so SSL context new. SSL context is equal to context new. And this thing we have to free at the end, I think. Freeing the SSL object, or do we have to free? Do we have to free the context method as well? Context new. Should not be changed after this used to create any SSL objects or from multiple threads concurrently. Is reference counted? Creating an SSL context object for the first time increments the reference count. Freeing the SSL context decrements it. Okay. So we have to free it. So SSL context free. SSL context new. This is the TLS server method. Can it return 0 or null? Okay, so it can be null. So if not context, then return -1. Okay. So now we have a context. And this context probably has to be handed to the threads. So handle get request. No, handle requests. So this gets an SSL context star context. Handle request args context. configure server context. So this needs to be configured now, probably. So they create context, and then they configure the server context. Serve. Now they configure it. Configure server context. SSL context use certificate chain file. And cert file path. And if this is less than 0, less than or equal to 0, then we want to return -1. Okay. And we also want to say SSL context use private, what the fuck, private key file context private key path SSL file type PEM is less than or equal to 0, then we return -1 as well. So we configured this context. Now we have to somehow get these cert files. We create a socket, and every time we accept, we create a new SSL object. So in the handle requests, every time we accept, we create a new SSL. So where did they define SSL? So SSL. So they initialize it to null. Maybe I should do that as well. And also in the serve, SSL, and when we accept, we say SSL is equal to SSL new with the context and probably the socket. SSL. We create a new context and we set, so if exactly this, SSL set file descriptor SSL, and then the client socket descriptor. And if this is not return, no, this is go to close client socket SSL accept. So if SSL accept SSL SSL read. After closing the connection, do we have to free it? Clean up for next client. Okay. So, and this is now an SSL read, if I'm not mistaken. And it also now gets the SSL object and not this thing. And when we write, so the response writing is unfortunately a little bit shitty now. Let's leave it like this. Okay, so let's say that we pound define read. So if TLS and if else pound define so if we have TLS, we define this as SSL read and write as ABC SSL write. SSL write also takes three things. A, B, C. We say read is just read. So if TLS, then we overwrite this. And we also say this is the, maybe not the FD, but some sock. So let's say this is the, so this can either be a file descriptor, socket reference, the right, maybe we call it the right handle, right handle. And type def right handle and this is an SSL. Else type def right handle I32. So down here, so this is obviously something that we only have to do when, so if TLS and if also this is if TLS and if read yeah, so there's no real point in doing so, I guess. So if TLS is there something like an SSL? No, there's only write. So we probably have to migrate this to use write. So now make file. Else client. So we have to free the context. Okay, so maybe we should do it differently. And pass other C flags. C flags. This is getting messy. But this way we can build the application with TLS and not TLS. I hope, at least. Man. No! We almost have it. So let's move SSL echo dot dot and arm the large file. And then go into the main.cpp and now why do we have both of them open? Main.cpp. The question is now, we probably also have to link against OpenSSL. So that probably won't work. So if TLS and if make HTTP server debug mode 1 C flags D TLS 1. No, TLS 0. I'll make clean SSL context free SSL context if TLS and if and also in the args here we have to define that also TLS and if and also here yeah we also did that. Okay, TCP proto obviously if TLS and if shutdown if TLS and if write response cannot be used as a function. What? FD was not declared in the scope. Okay, so let's call it FD for now. Okay, okay. So that still works. That still works. Can we check maybe if it contains something? if the C flags contain something, check if make argument contains string. Text functions. Here are some functions that operate on strings. Okay, we can look at this in a second. I have to be right back. Okay, so I think we're gonna fix the build system now. Find string. Find string. Searches in for an occurrence or find. If it occurs, the value is find. Otherwise, the value is empty. Test of the presence of a specific substring in a given string. Returns all white space separated words in text that do match of any pattern word, removing any words that do not match. Sorry. What I want to do is, if the C flags contain debug mode, so find string. Is there some example? Performs a textual or simple way to get the effect of the pad subs. Second shorthand simplifies. What does it return? Find string. You can use this function in a conditional to test for the presence of a specific substring in a given string. So find string. We try to find debug mode. One. So if debug mode, then we compile with -g. Or let's say, so if this O flag is equal to O flag is equal to G. O flag is equal to this. I don't know if this even works. And let's say O flag. Variables in make file. Is that correct? Defining how variables get their values. Basic variable references. So O flag is equal to nothing. Now O flag is equal to dash G. O flag. So we don't need this. O flag. Oh no. O flag. Yank F this. VFG paste. Yank F this. So we can record a macro, I guess. So QQ. Look at this. So down F dash VFG delete insert O flag Q. Oh, so this was not even right. Okay, so look at the macro. So now the macro. QQ delete F dash delete FG. Shit, wrong. So QQ delete F dash DFG insert O flag escape 3DD. No, one down 3DD. Q. No. What? Okay, one last try. So delete F dash DFG insert O flag escape one down 3DD. Done. Nice. So what now? So make C flags as equal to dash D debug mode to 1 dash D TLS is equal to 0. Okay, so this in C flags. Missing separator. C flags make. Okay. How do we do this? Missing separator. So this doesn't work. Missing separator. Where is a missing separator? Okay, so we could also do something like we could define our C flags. If you define it first with so if debug mode conditionals in make conditional directive if equal, so it's if equal debug mode 1, we said O, so we said O flag to nothing, O flag is equal to -g. So if equal TLS 1, now we set C flags so this could also be part of the C flags. So let's say C flags equal to nothing. If debug mode, we say C flags plus equals G. And C flags dash D debug mode 1 C flags plus equals dash D TLS 1. Invalid syntax in conditional. What? If define, if not equal, if equal, and if. What? If equal. in line 3, if equal TLS do we have to do like this? Still wrong. arg1 maybe it doesn't like the tabs here. No. Okay, so that works. What happens if I don't define this? Okay. Make okay, so then it just but it also works. So probably we don't need this. Okay. So this works. So make debug mode 1 TLS 0. Okay, nice. So we cleaned that up. Let's get back into our write response. So this now probably needs an arena allocator. I don't like this because we now have to use write. We now have to use write in order to write to the socket, because OpenSSL uses write and not fwrite. Also, I don't like this here. But I think we have to do it like this. Yeah. So for this, we probably need an arena allocator. The right handle. So we don't do this anymore. Okay, so this is something we don't do anymore. We need probably some buffer. And this, our response buffer. Response buffer. I don't know if this is even something we want to do, or if we can factor this out. When we could look at the largest response we have to make. This is more or less a vector now. I mean, we have a max HTTP message size. So this is, let's call this the request buffer. And we probably want for each thread to have its own response buffer. And the response buffer obviously is a restrict keyword. My internet's gone. Hello. No. Restrict and see. So the status line so we need something like stir and copy. Or something like mem copy into the response buffer and from the status line with the size of the status line. And n left is equal to the size, so maybe make it a const char. And left, this is just the max HTTP message length, and left minus status minus equals status, size of the status line. But this includes the zero, the null terminator. We don't have this method right now. don't want to implement this. My own. What if we just implement a buffered writer? Buffered write.cpp. Buffered read. I don't know if we should do it, but let's just do it. If not, define buffered. Why did I call it buffered read? Buffered write. If not defined, buffered write. And if struct buffered writer or maybe we just call it the we put it in HTTP. Maybe we put it in HTTP. Let's say struct buffered response writer. And here we have a car the buffer, and that is max HTTP message size length. Something like void reset buffered response reset. We have something like push stir. Push string. Can fail. The question is, maybe push const stir. this is just a constant pointer, but or is it a pointer to constant? No. So reset. Also, we need an init. Writer offset, writer. I think we don't need anything else. Maybe we have to buffer 0 initialize these as well. Oh no. No, we don't have to do this. And we need a length, so writer length. Okay, in string.h we now introduce a i16 stir and copy. And it has 2 core stars and a usize. Okay. Why do we need standard IO in this file? I hope we don't need that. So push string, push stir. Stir and copy. Writer buffer plus writer offset the stir and with a restriction of a writers, so the left do we need a length? Or is it just, I don't even think we need a length here. Stir and copy. And left. The writer plus HTTP max HTTP message length Should we store the offset in? I don't know. So it's minus this plus, so current, let's say car star, current pointer is equal to writer buffer plus writer offset current pointer. And left. So this is the current pointer. If the current pointer current pointer car star end pointer buffer plus HTTP message length. If the current pointer is greater than or equal to the end pointer, no. Current pointer plus stir len return -1. Otherwise, we say memcopy into the current pointer. And we also forgot to increment the i16 red val is equal to this. Now, if this is equal to -1, return -1. Otherwise, offset plus writer offset plus equals so i16n is equal to this. If n is equal to -1, return this. Offset plus equals n, return 0. We could store this inside the struct. So this is something like use size and left and remaining. So we could say something like n remaining. So writer n remaining is equal to max HTTP message length. minus equals n. If n remaining is less than strlen memcopy current pointer str pointer str length. Okay, now we have to implement str copy. Str n copy. Say for. So this is the destination, this is the source, and this is n. For int I is equal to 0, I is less than n, plus plus I, plus plus source, plus plus dest. If star source is equal to the null terminator, then return zero. Do we copy the null terminator? No, we don't. Str and copy, so star dest is equal to star source. So HTTP so push string, push stir. We now have okay, so now we say our buffered response writer we init this this wants a buffered response writer okay, and here we now say push stir writer and the status line. If this is equal to -1, return -1. If reason and push stir reason writer reason is equal to -1, push stir writer CRLF so this would be the bytes written. push stir, no, push string now. Push string. Writer, the field name. Push string. Push car. Something we have to writer. So this is another push string. Writer and the field value. And push stir. The CRLF. And push string. We don't even need to close this one. We now have to say write to the right handle. How did I call it? The buff, which is the writer buffer, and the writer offset. Okay. So this should now work for both. And push string writer. Okay. So now let's verify that we actually do stuff correctly. So push string. Here we also forgot to increment the offset plus equals the stir length and n remaining n remaining is something we don't really have to keep track of, but push car. This is the current pointer. If n remaining is less than 1, otherwise we say star current pointer is equal to C. Plus equals 1 minus, so plus plus minus minus. Here we also have to reset our writer. How do I call it? Yep. We could also make something like a const card where we know the size. HTTP. So push car and push const stir. HTTP. I think this will look a lot like this. Const car stir is equal to size of stir. Stirlen. This is the just the stir. This is the stir size of stir. Size of stir. Size of stir. Okay, push stir. Push const stir. Okay. http.cpp blah 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 reset. I wonder why that why okay. Reset. push string, push string. Wonder if this works. I don't believe this works, but can we just get the size of this? HTTP. Two, 4, 2. Oh. So what I think we just do is disregard this here. And just cast this to a car star. Say this is a push stir, push const stir. Using const here, discarding the const here might cause performance issues. Wonder if it okay. -x get localhost 8080 index.html. Received HTTP 0.9. Not allowed. So there is a bug, yeah. Push stir. Status line. So let's say GDB HTTP server break write response single stepping. So stir and copy. Push stir. Then we write a CRLF. Field name, push car this. Push car. Push constir, push stir. Oh. That was not the intended behavior. So if the first one, yeah, return I. Port 8080. Binary output. Okay, so there is some bug. Offset is 0 at the very beginning. I wonder why we can't really debug this. Make clean. Break at right response. Okay, now it works. Okay, P the writer. HTTP 1.1. Nice. HTTP 1.1 200 carriage return line feed. Okay. Write response. That could have been something. Okay, so the push construct, just remove it. This doesn't work. Nice. So this works. The question is now, can we do this with TLS 1? No. So TCP proto was not declared. TCP Pro. Okay. Private key path, cert path. Key.pam and the cert path cert.pam. The kill mute. Cert path. Okay. Crosses initialization of red bytes. Why does that only apply to the when TLS is Okay, that doesn't even make sense. Does it? Jump to label, close. Initializing argument 1 of TLS. Okay, so if TLS write response SSL same thing here. I don't quite get where the difference is. Oh, because we say go to close client socket. Okay, so then I32 read bytes. Into 5.4. Ooh. So this is also if TLS else SSL and if. I think we have that somewhere else as well. Yeah, here. So if TLS else and if SSL okay, so now we have to link against it. So if this dash D no plus equals dash L open SSL. Link against open SSL. LSSL. LSSL. Okay, it does compile, but it also just fails. So git add git commit added TLS support, but it doesn't work yet. I think this is a good place to stop for today. We haven't really caught all the errors. There's probably a lot to do. I probably won't be live tomorrow, but maybe on Friday. We will see. Thank you for watching. Have a nice Christmas.